Morning students. Today's topic is the calculations involving in the units and dimensions. Till yesterday we finished that calculation of the packing efficiency in the unit cells. Is it fine? So today the another type of the calculations involving in the unit cell. So let's see that. First of all, we'll see that the density of the unit cell. Density is equal to mass of the unit cell divided by the volume of the unit cell. Mass of the unit cell and the volume of the unit cell. Okay, the whole unit cell will be taken, its mass to be calculated and the volume should be calculated. Okay, we know that the volume of the unit cell will be taken as an A cube. Is it fine? So this can be substituted here. Now we need to calculate the mass of the unit cell. The mass can be calculated. You know that the unit cell is made up from the particles. Okay, so the whole unit mass will be depending upon the number of particles. Is it clear, students? So here we will see that mass is equal to number of particles into mass of each particle. Okay, so total number of the particles, suppose 8 particles are there and the mass of the particle is x, so that will be total mass will be 8 into x, 8x. Is it fine? So here the mass will be calculated as mass is equal to number of particles will be denoted as small z, and mass of each particle will be taken as small m. So it will be the mass of the unit cell and this will be the mass of each particle. Are you getting me? So now substitute this value here. So you get the density is equal to, what is the mass? Z into m divided by, that will be your A cube. Okay, so now how will you calculate the mass of the particle? The main thing is that the mass of the particles also to be calculated. So the one formula is that mass of the particle will be equal to molecular mass or molar mass divided by the Avogadro's number. Okay, so we can calculate the mass of the particular particle. How will you calculate? The molecular mass divided by the number of particles, number of moles. Is it fine? So now substitute it here. So rho is equal to, that will be Z into capital M divided by A cube into ME. So this is the density formula. So density is equal to number of particles present in the unit cell. Okay, if it is a primitive unit cell, then 1, and if it is a body-centered cubic unit cell, then it will be 2, then if it is your face-centered cubic unit cell, then it will be 4, okay, and end-centered 2. And the mass of the molecular mass of the whole compound, and A cube is the that will be the volume of the cubic unit cell, and the Na is the Avogadro's number. So by just substituting all these values, we can calculate the density of the particle. Okay, beta. So now this was the first part. Now the second part is coming that you know that we have discussed that the crystals are somewhat perfect structure, but if you study in the deeper part or in the detailed part, is it fine? Then you will find out that the crystals are not 100% perfect. Almost we can say that not 100% means a few of the crystals are showing the certain defects in them. So we need to find out the defects of the crystals. Is it fine? Yeah, defects in the some arrangement of the particles or something like that. So the next topic is the imperfections in the crystal lattices. Yeah, imperfection in the crystals. Okay. So we are finding out the defects in the solids, and that topic is the imperfections in the solid. Okay, beta. So these are also known as the defects basically, and there are two types of the defects. Suppose in the crystal lattice, if there is a defect in the only particle, only 1 or 2 particles, then it is called as your point defect. Suppose I have made that whole line in which only one particle is varied. Okay, there is a difference in the 1 or 2 particles. Is it fine? So in that case, it is coming as a point defect. Okay, beta. And if the whole row is having certain defect, whole row means like the particle arrangement is there and the whole row will be having the certain problem, then this is called as a line defect. The line defect is not in the course, it is just simply to classify that imperfections of it that was taken. So if the whole row is having any defect, then it is called as a line defect, and if it is only defects in the particles, the particle arrangement or the particle numbers, etc., then it is called as a point defect. Okay, beta. So we have to describe only the point defects in this portion. Okay, so the point defect can be classified into the 3 main parts. The first thing is the stoichiometry defect. What is the meaning of the stoichiometry defect? In which, this is a kind of defect in which the particles will be shifted from one place to another place. Okay, but there is no change in the number of the particles. Is it fine? Suppose initially when the crystal was made, and you see that the total number of the particles were 100. Okay, so after arrangement of these 100 particles, the number of particles remain 100 only. There will be neither 101 nor 99. There is no change in the number of particles. Is it fine? So only the shifting of the particle takes place. Then it is called as a stoichiometry defect. And this is happening because of the temperature variation. If there is a change in the temperature, then it is called, also known as the intrinsic defects or thermodynamic defect. So this can be considered as two types: stoichiometry defect plus, you can say this is intrinsic defect, or it can be considered as an thermodynamic defect. Okay, beta. So this is happening because of the heat energy. Second type of the defect is there. Okay, that is impurity. Impurity means if the particles are replaced by the another particles. Are you getting me? So suppose X particles are replaced by the Y particles, and Y particles have been introduced from the external sources. Okay, so then this is called as an impurity. Due to which the defects are arising, these are called as an impurity defect. Now coming to the third one, that is a non-stoichiometry defect. This kind of the defect in which what happened, the number of particles will be changed. The stoichiometry numbers will be changed. So I told you that if initially when the crystal was made and the 100 particles were there, so due to the certain reason, the number of particles may be either 99 or 101, something like that. Okay, so variation in the number of particles, and this, if the number of particles will be changed, then this type of defect is called as a non-stoichiometry defect. Non-stoichiometry defect will be taken later on. Now come to the stoichiometry defect. Stoichiometry defect can be seen in the two type of the compounds, that covalent compounds as well as an ionic compound. So for the covalent compound, different names are there, and for the ionic compound, different names are there. So we have to describe each and every point. So let's start with the first one. If it is present in the covalent, if it is present in the covalent compound, then it will be of two kinds. Suppose this is vacancy defect and the interstitial defect. Suppose in the unit cell, so a number of particles are like this. Okay, so one of the particle or one or two particles will be removed from there. Removed means they will be shifting in the another unit cell. Is it fine? So they are creating a vacancy here. Is it fine? In that case, what happens? The density variation will be there. Then the density will be decreased. So per unit volume, the number of particles will be less in the particular unit cell. Although in the whole element, the number of particles will be same. Are you getting me? But in the particular unit cell, the number of particles is shifting in the another unit cell. So if it is replaced from one unit cell, then it is creating the vacancy and the density will be decreased. So such type of the defect is called as a vacancy defect. Now the same thing is that the second type, that is a interstitial defect. Interstitial defect is a kind of defect in which what happened, suppose the particle has been removed from here, and where this particle will go? If this particle will go in the another unit cell. So here you will see that one more particle is present between the interstitial sites. Okay, and the space present between these particles, the particle will be present. So in this, you will see that the density will be decreased, but in this kind of the unit cell, you will see that density will increase. So this type of the arrangement in the particles, but no change in the number of particles, such type of the defect is called as the stoichiometry defect, but it is seen in the covalent compound. Now come to the ionic, this one. In case of ionic compounds. Okay, so there are two types of the defects seen. One is a Frankel's defect and second is a Stretchy's defect. In the Frankel's defect, what happened? This defect is arising due to the size of the cation and the size of the anion. In compound, the anion size is bigger and cation size is smaller. So small size particles can easily move in the unit cell. You can see that if you talk about this one. So this is a positive, negative, negative. Okay, then it is negative, then positive, then it is negative, and this is positive, then positive, negative, positive, and negative. Understood this thing? This is the arrangement of the particles. So you know that. So one of the positive particle will be moved from this side, and it will come in the interstitial side. So here it is creating the vacancy, and here it is creating the interstitial sites. So in the same lattice, you will see that particles will be moved from one place to another place, but there is no change in the neutrality. Neutrality will be maintained. So such type of the defect is seen in the Frankel's, seen in that ionic compound, and it was described by the Frankel. So it is called as the Frankel's defect. Okay, beta. Now coming to the Stretchy's defect. In that case, you will see that if there is a positive charge and negative charge, positive charge and the negative charge, negative, positive, negative, positive. Positive, negative, positive, and negative. Suppose from the one unit cell, one positive ion has been replaced. Replaced means it has migrated. Understood this thing? So along with that, one negative charge will also be migrated. So one positive and the one negative will be moved in the another unit cell. So it is creating the 100% vacancy. Vacancy of this place and the vacancy of this place. But here you will see that vacancy and interstitial both will be seen. But here you will see that if one cation will go out of the unit cell, then another anion will also go out. But neutrality will be maintained. So here the density variation will be there. Here there is very less density variation because the particles remain in the unit cell, but here you will see that the huge density variation can be observed. Neutrality will be maintained. So such type of the defect is called as an Schottky's defect. Here AgCl, AgBr, etc. Okay, this can be here also AgCl can be taken. Okay, so many other examples are there. You can see that Schottky's and the Frankel defects are seen. Now coming to the impurity defect, in that case you will see that the metallic particles will be replaced by the another metals. Is it fine, student? So let's see that one example. Suppose it is an Na plus and Cl minus, Na plus and you will see the Cl minus, Na plus and Cl minus, and this one will be your Na plus and the Cl minus, and this is your Na plus and Cl minus and Na plus and the Cl minus. Okay, this is an NaCl compound. Suppose here you will see that two Na particles, two Na ions will be removed from that. Okay, so how many positive charge has been removed from that? That will be plus 1, plus 1. Okay, so that will be plus 2 charge will be removed from that. So, but you need to show that the neutrality should be maintained. Instead of it, suppose the strontium comes. Strontium. So strontium is only one particle, but the charge is having 2. It is having the two positive charge. So neutrality will be maintained and the particle will be replaced. But this will be creating the vacancy. Is it fine, student? So this can be seen in that impurity will come, but the neutrality will be maintained. So such type of the defect is called as an impurity defect. I hope you all understood this thing. Now coming to the next one, that is your non-stoichiometry defect. I told you that there will be change in the number of particles. Okay, the number of particles will be changed. So this is called as a non-stoichiometry defects. Now, how many type of the non-stoichiometry defects are there? There are 2. The one will be the metal excess defect and the second will be your metal deficiency defect. What is the meaning of the metal excess? The number of metallic particles will be increased. The number of metallic particles will be increased in that is called as a metal excess defect. And here metal deficiency defect means what? The number of metallic particles will be decreased. I hope you understood this thing. So these are the 2 things which you have to see that. So let's see, देखो, metal excess defect can be because of the 2 things. The one will be the due to the anionic vacancy and the second will be the due to the presence of the extra cation. So this is your metal excess defect will be due to the anionic vacancy and due to the presence of the extra cation. Okay, so let's describe this thing. Okay, so I just rubbed it. Okay, so without any wasting of time, let's start. Metal excess defect due to the anionic vacancy. You know that if the NaCl is a compound, ionic compound. If it is heated in the sodium vapors, then what will happen? If the NaCl will be heated in the sodium vapors, then what will happen? So here you will see that one of the chlorine ions, suppose any of the chlorine ions, see this Cl minus is there, it will move from here and it will come to the sodium vapor side. And what it will do? It will donate 1 electron, okay, 1 electron, and it will be neutralized. So this neutral Cl will come this side and it will be leaving behind that 1 electron here. Are you getting me? Instead of the Cl minus, 1 electron will be left. Okay, so this electron will be there and it has replaced the Cl minus ion. Neutrality is maintained, but instead of the Cl minus, 1 electron is there. Now what is the use of this electron? You will see that if like any light energy is incident on that, and then this electron will absorb the certain wavelength of the light energy. Is it fine? And it will get excited. When it comes back again in the normal position, it will emit the certain wavelength of the light, and this will be the yellow color. So that's why the whole crystal of the NaCl will be visible as yellow color, and this is called as F center. F center. Understood? F center, or that is also known as a Farbenzienter center. It is also known as a Farbenzienter center, or it is also known as a color center. Color center. So there can be the 3 names. Okay, so that Cl minus will be replaced by the 1 electron, and this Cl will go upside, and this Cl will react with the sodium, and it will form again NaCl this side. I hope you understood this thing, beta. So this is called as an due to the anionic vacancy. The anion has migrated, so vacancy has been created. Okay, beta. Zn2, and when it is heated, then it will be converted to Zn2 plus half O2 and plus electron will be liberated. So the second type of the defect is metal excess defect due to the presence of the extra cation. You will see that if Zn2 is heated, then it will be converted into the yellow color. Okay, but when why is it so? Because some amount of the oxygen is liberated, anion has been liberated, and automatically you will see that the extra cation will be present in case of the zinc oxide. The zinc is an cation. Okay, so this will be the anionic vacancy, because anion has left one electron here, and this one you will see that anion has liberated, but leaving behind the zinc ion. Okay, so this is creating the presence of the extra cation. And the last one is your metal deficiency defect. In that case, you will see that metal will be deficient. There you will see that if I give you the one example, FeO, generally we write FeO as 1:1 ratio, but if the F is written as 0.93 to 0.960, so it is your non-stoichiometry. Okay, so last year you have seen the non-stoichiometry hydride. The same thing you will see that if the metal will be deficient in the compound, then such type of the compounds are there. That means it's not in the whole number, it will be in the fraction. Okay, so such type of the defect is called as a metal deficiency defect. So these are the various type of the defect, students. You need to read through the textbook, from the textbook, and write down the notes. Is it fine, student? Okay, that's all for today. Have a